You've been here. You know exactly what comes next. You draw a triangle. You say, cap theorem. You pick two corners. You explain why your system is CP or AP. The interviewer nods. That answer is built on a framing that the inventor of the cap theorem himself described as misleading. Not wrong, incomplete. In 2012, 12 years after introducing cap, Eric Brewer published a follow-up paper. This video is about what that paper says and how we should think about cap. Why the PIC2 model misrepresents the real design space. What cap ignores that is very relevant in software design. And why a design principle from a 1987 paper is now foundational in modern distributed systems. Consistency, availability, partition tolerance. At most two. The traditional framing sorts every system into one of three zones, and we have been taught to pick our zone at design time and stay there. CP, consistency over availability when nodes can't agree. Wrong answer is worse than no answer. Zookeeper, etcd, hbase. AP, stay available even during a partition, serve stale data if needed, sort it out later. Cassandra at default settings. And CA, and this is where we have a problem. CA is supposed to mean you've given up partition tolerance. Single node databases, Postgres on one server, fine. The problem is when someone applies that label to a distributed system. Partitions aren't a design parameter you choose. Networks fail, machines crash, cloud regions go down. Calling your distributed system CA doesn't change any of that. It just means when a partition arrives, and eventually one will, you'll be making decisions under pressure that you could have made deliberately. But the CA corner isn't even the deepest problem with the PIC2 model. Brewer's paper identifies three specific ways the framing causes engineers to build systems worse than they need to. The first problem is that all three properties are treated as binary. You have them or you don't. That's not accurate. Availability isn't on or off. Production systems target 99.9, 99.95, 99.99, different points on a spectrum. Consistency is also a spectrum. Linearizability at one end, every operation appears instantaneous, globally ordered. Eventual consistency at the other, writes propagate everywhere eventually, but there's no bound on when. Even partition isn't clean. A 200 millisecond hiccup, 2 seconds, 10 seconds? The answer depends on your timeout. You don't detect partitions, you define them. The triangle collapses all of this nuance into three dots. Real systems live inside the triangle. The PIC2 framing makes you think there are only three valid positions when there are actually thousands. The second problem, the theorem only describes behavior during partitions. It's silent about what to optimize for the rest of the time. And partitions are rare. The vast majority of the time your network is fine. Cap says nothing about those hours, days, weeks.
Brewer's updated framing. Maximize both during normal operation. Make a trade-off only when a partition is actually detected. That shifts cap from a permanent identity, where AP, into a runtime decision you make when specific conditions occur. The goal isn't to pick a corner and live there. It's to run at full capability most of the time and have a real plan for the cases where you can't. And most teams don't think through what their system does when it can't have all three. Not because it's hard, because it's uncomfortable. Because it means accepting your system will sometimes be inconsistent, and designing for that deliberately instead of discovering it at 3 a.m. That's the question Brewer's paper is really asking. We'll look at different answers to it, what to do during a partition, how to recover, how certain data structures can sidestep the question entirely, how to build architectures where the question rarely comes up at all. But before that, there's a variable cap doesn't mention at all. And it's relevant in most database configurations, replication settings, and timeouts we tune. Something is absent from the cap theorem: latency. And the essence of cap plays out during a timeout. Node A writes data, sends a confirmation request to Node B, and waits. Node B is slow, high load, network congestion, or a real failure. From Node A's side, there's no way to know which.
At some point, node A has to decide. Cancel or keep waiting, availability suffers. Proceed without confirmation, consistency is at risk. There's no option C. Waiting indefinitely is just choosing consistency with infinite latency. A partition isn't a separate failure category. A partition is what you call it when you've decided to stop waiting. It's a timeout with a name. CAP's silence on latency is what motivated Daniel Abadi to propose an extended framework, first sketched in a 2010 blog post and formalized in a 2012 paper. He called it PACELC. If partition, choose between availability and consistency. Else, during normal operation, choose between latency and consistency. That second line is what CAP was missing. Even when everything's fine, there's still a trade-off between how fast you respond and how confident you are in the data's freshness. DynamoDB makes this unavoidably literal. Strongly consistent reads cost twice as many capacity units and are slower. Amazon is charging you for consistency. That's PACELC expressed as a line item on your cloud bill. Every read preference you've set in MongoDB, every Cassandra consistency level you've configured, every time you chose async replication over sync, you are making a PACELC decision. This brings us to the most practical idea in the video, a design pattern from Brewer's paper that most of us don't implement. Most distributed systems are designed for exactly two states. Normal operation gets careful engineering. Load balancers, read replicas, caches, health checks, all of it tuned for the common case.
The broken state gets retry logic, generic errors, and eventually an on-call page. What's missing is a third state, not generic failure, but a specific designed state with its own rules. Normal mode, everything connected, optimize for the common case. Partition mode, a node is unreachable, detected deliberately, not through a generic error handler. Logic that says, this is a partition event, switch to different rules now. Recovery mode, the partition healed, nodes reconnected, but they've been running independently. Their states have diverged. This is not a return to normal mode, and treating it like one can cause problems. You have two histories, operations that happened on both sides while they couldn't see each other. Some of those operations may have already been shown to users. You can't quietly undo them. Merging those states is recovery mode's job, and it requires having designed for it before the partition occurred, not during. The way to design partition mode intentionally, go through your operations one by one and ask, what should happen if this runs without access to the rest of the system? Reading a user profile, nothing breaks. Serve from local cache, allow it. Registering a new email, must be globally unique. Can't verify that right now. Block it. ATM withdrawal, balance could go negative, but you can bound the damage. Allow up to a limit. Charging a credit card, external action, can't undo it. Queue it for after recovery. Different operations, different answers. Same system. Writing this table for your actual system almost always surfaces decisions your team has been making implicitly for years. That's usually worth more than the document itself. That ATM row isn't hypothetical. It's a real production system making this exact trade-off, and it's a good illustration of how to actually answer the main question. When was the last time an ATM refused your withdrawal because it couldn't reach the bank? Probably never. And that's not luck. It's a deliberate architecture choice. An ATM has one core invariant. Your balance should never go below zero. If you apply strict consistency, whenever the ATM can't verify your balance, refuse the transaction. No cash, come back later. For a machine that's supposed to give you convenient access to your money, that's a problem. Instead, ATMs enter what Brewer calls stand-in mode. In stand-in mode, the ATM stops trying to achieve full consistency. It applies a simpler rule. Allow withdrawals up to a bounded limit, record every transaction locally, and keep serving.
When the bank connection is restored, the ATM uploads its log. The bank reconciles. If your balance went negative during the offline window, an overdraft fee is charged. The bank doesn't prevent every mistake. It bounds how large a mistake can happen, detects the violations when it reconciles, and compensates afterward. The overdraft fee is the answer to what does your system do when it can't have all three: accept the operation, bound the risk, detect the problem, make it right. That's the design.
You can see it in most consumer apps you use. A ride-sharing app confirms your booking before the driver has explicitly accepted. An e-commerce checkout accepts your payment before inventory is confirmed reserved. An airline issues your boarding pass before every downstream system is caught up. A food delivery app confirms your order before the restaurant accepts it. Every one of these systems is making the same bet the ATM makes: move forward, bound the damage, reconcile afterward. So far, 2 answers to the central question: design for 3 states, not 2, and bound the risk like the ATM does. Both assume the trade-off is unavoidable. For most operations, it is. But for certain kinds of data, there's a completely different answer: design the data structure so the question doesn't apply. For certain kinds of data, you can design the data structure so concurrent updates from multiple nodes always converge to the same result, regardless of order, without any coordination. That's what a CRDT is. The keyword is converge, not agree in advance, not coordinate, not lock. Converge after the fact, always. A concrete example can be a YouTube view counter. Multiple servers in different regions incrementing it simultaneously, no locking, no coordination. It never loses a count. Why? Addition is commutative. Order doesn't matter. Each node tracks its own increments, merge by summing, and you've mathematically eliminated the race condition. There's no wrong order. Every order gives the same answer. For a data structure to guarantee convergence, commutative, order doesn't matter, idempotent, duplicate messages don't corrupt state. Guarantee both, and the trade-off disappears for that data type. You're not choosing between C and A anymore. The math handles it. There are 4 common CRDT types. Take a few seconds to read those. The view counter we just described is the PN counter, top left. A claim you'll see repeated is that Figma is built on CRDTs. It's worth being precise because the actual story is more interesting. Figma's canvas isn't built on true CRDTs. Their server is a central authority. What they borrow from CRDT research is last writer wins register semantics. Each design property has a simple conflict rule. The server serializes the rest. True CRDTs are for fully decentralized systems. Figma has a server, so they took the useful idea without the overhead they don't need. Pragmatic design, just not the same thing. Their code layers feature in 2025 went further, using Eggwalker, an algorithm that temporarily constructs a CRDT structure to resolve text conflicts and then discards it. The space is still evolving. Redis Enterprise uses true CRDTs for geo-replication across data centers, real convergence guarantees, no central coordinator. GoodNotes ships auto-merge to its millions of monthly users. The other rows, Figma Canvas, Notion, Apple iCloud, are CRDT influenced, not full implementations.
CRDTs handle one answer to the central question, for certain data types, mathematically. But most operations aren't like that. When something fails halfway through a multi-service workflow, you need a different approach, and there's a decades-old formal solution most engineers are already using without knowing its name. The ATM was doing something specific. It accepted the operation, bounded the risk, logged everything locally, reconciled and compensated when connectivity returned. That structure, accept, bound, log, compensate, has a formal name, and this is running in most distributed systems you work with. Formally described in a 1987 paper by Garcia Molina and Salem and discussed by Brewer in the context of partition compensation, they called it the Saga. Traditional database transactions assume you can hold a lock on everything involved until the whole operation either commits or rolls back. One database, one machine, that works. Across multiple services over a network, holding a distributed lock creates a reliability problem. Service A holds a lock waiting on B, B waits on C, C is slow. Everything stalls.
Under production traffic, this cascades. The Saga breaks this. Instead of one transaction spanning everything, a sequence of small, local transactions, each commits immediately, no distributed locks. When step 3 fails, the compensation path runs backward. Refund the card, cancel the order. The correctness guarantee isn't all or nothing, it's that the net effect of everything, including compensations, leaves the system in an acceptable state. A refund is not the same as never having been charged, but for the business, it's equivalent enough. You've already seen this. It's exactly what the bank does with the overdraft fee. Every e-commerce checkout is a Saga. Every loan approval that touches multiple services is a Saga. Every subscription sign-up that needs to create accounts, charge cards, and provision access is a Saga. The pattern predates microservices by decades because the problem predates microservices by decades. The paper is from 1987. The problem it solved is the one you're solving now. It just has better tooling. CRDTs eliminate the trade-off for certain data. Sagas answer it for cross-service operations. Both assume the network is sometimes unavailable and design around that. There's one more direction this thinking goes. Let's look at that. Let's consider a question. What if partition mode wasn't the edge case you designed for, but the state your app always runs in? Most applications treat the server as the source of truth. Every read, every write, every operation goes through it. Which means the network is in the critical path for every operation. When the network is slow, the app is slow. When the network is gone, the app is broken.
Local-first software inverts this. Data lives on your device. The server is a sync coordinator, not an authority. The network is used to exchange state between instances when it's available. Every read and write hits a local database. No round trip, no spinner. Not fast, instant. The application works completely offline because there's no difference between offline and normal. Partition mode isn't a degraded state, it's just how the app runs. When devices reconnect, CRDT-based sync handles the diverged state in the background. Recovery becomes routine infrastructure, not an incident. That sync protocol that handles diverged state when devices reconnect, that's the partition recovery problem Brewer was describing in 2012. Still the same engineering challenge, but they're now tools, YJS, AutoMerge, purpose-built sync engines designed specifically for it. We now live in a world where your Notes app works at 35,000 feet, your issues are available when the Wi-Fi drops, and everything syncs when you land without asking you to do anything. That's not a pleasant UX feature. That's partition recovery built into the architecture from the start. So where does this leave you? The CAP theorem is still a useful tool. The triangle is still in interviews, but knowing what it describes and what it doesn't makes you a better engineer. Saying we're AP labels one property of your system under one failure mode. It doesn't answer what operations run during a partition, how you recover, which invariants you protect, or what happens when something inconsistent has already reached a user. The architecture work starts after the label. Consistency isn't a global dial. Cassandra lets you set it per query. DynamoDB prices it per operation. A user's profile photo doesn't need the same guarantee as a financial right. Your system should reflect that. That operations table, which behaviors are allowed during a partition, which are blocked, which are queued, is worth writing for your actual system. The exercise surfaces decisions your team has been making implicitly for years. These are the questions the CAP theorem forces you to ask. They don't have clean answers, but it's better to think these through than discovering the answers during an incident. Link to Brewer's paper and other references are in the description. If you find this useful, please like and share. Thanks for watching and see you in the next one.